fast forward in 2024, and it seems like every other day we are seeing a more capable and dexterous robot, particularly in the humanoid space. So the hardware has clearly gone so much better. And the robots are even improving in their manipulation and dexterous manipulation capabilities. A lot of the tasks that we thought a couple of years ago a robot would not be able to do, they're able to do now thanks to data-driven techniques. So given these fast advances in robotics, a fair question to ask is, where is my general purpose robot? How far or close are we to that goal? And to understand that, I feel it would be useful to try to visualize what living with such a robot would be like, and then we can assess how far we are from that goal. Thankfully, we don't have to use our imagination for that. Researchers at Stanford created a video about 10 years ago where they teleoperated the PR1 robot, the predecessor of the more famous PR2 robot, to do a variety of tasks in the household to just show what living with a robot would look like. Broadly speaking, you can see that the robot would need 3 distinct capabilities to make this happen. First of all, the robot would need to have dexterous and capable manipulation skills, which allows it to interact with the environment, pick up tools, and use tools. The robot would also need long horizon planning capability so that it can execute abstract tasks such as tidy my room. And finally, the robot would need to be able to interact with humans, not just through language, but also physically. So because these capabilities are so crucial, I'm going to try to organize them in terms of increasing difficulty and try to understand how far we are from achieving this dream. Motor skills are, of course, the foundation upon which all these capabilities will be built. So they lie at the level 1. Once a robot has sufficient manipulation capabilities, it can sequence those skills to achieve long horizon tasks. And finally, a robot that can achieve long horizon planning can be useful to humans by interacting with them and figuring out what they want to do. And that's a capability that's on the level 3. Most of the progress that we have seen in the last couple of years from data-driven techniques has happened at the level 1, whether it be diffusion policies or large behavior models from Google and DeepMind. The goal of this presentation is going to propose a way forward which may allow us to scale these motor skills to enable robots to level 2 and level 3. First, I want to talk about some of the projects that I did early in my PhD, which focused on long horizon planning. In particular, some of the early projects were based on search-based planning techniques, which we applied to a variety of domains, such as navigation, task and motion planning, and manipulation. And these planners relied heavily on hand-designed primitives and skills. However, with the right design of primitives, we found that these planners can be quite successful in achieving long horizon reasoning. In particular, the demo that I showed to you earlier was also using a search-based planner. On the left, you can see the robot searching using a hand-designed set of primitives to figure out a trajectory to reach to a pre-gasped location, and then execute a hand-designed pickup controller, which then picked up the box. So the biggest takeaway for me from all these projects was that planning is an extremely capable tool when it is coupled with the right set of primitives and skills which are appropriate for the tasks that the robot wants to solve. Right? So if we want to scale robots to do general purpose tasks, we have to scale up skill learning. And the key question I'll try to understand is where these skills are going to come from. And an obvious answer, of course, is to focus on data-driven techniques such as imitation learning and reinforcement learning. In particular, imitation learning has been quite successful in the recent years, where large amounts of expert demonstrations have become available, and robots are able to learn a variety of tasks directly from sensory inputs. On the other hand, reinforcement learning does not require expert demonstrations, but works really well when a good simulator is available and an expert can design reward function for the tasks. However, there is still significant reliance on a human who's choosing exactly which skills the robot should be learning, collecting demonstrations for those skills, and designing the reward functions in the case of reinforcement learning. And I believe that this reliance on humans during data collection is a major bottleneck which has to be solved if we want to scale up robots. So the main question I'll try to answer is how we can automate skill acquisition. And to this end, I'm going to propose that our robots should be doing task-oriented learning. That is, instead of a human designing and specifying what they need to do and what skills they need to acquire, a robot should be deciding on its own the skills it requires. In an ideal world, I would like to go to the robot supermarket, bring a robot home, and tell it to help me in my house. I don't want to tell the robot what exactly it needs to do. I want the robot to figure out on its own the task that it needs to do to make me happy. Perhaps my house is quite untidy, and I would like the robot to tidy my house, right? Based on the tasks that it believes would be useful to me, the robot should be able to figure out on its own the exact motor skills it needs to acquire to make those things happen. Right. Right. So to this end, in this thesis, I'm going to propose a plan to learn framework which enables a robot to autonomously acquire skills. And we will show that this framework is not just autonomous, but also enables more efficiency if the robot deliberately chooses exactly which skills it needs to do and what tasks it needs to do to achieve the given objective. All right. So the outline of the talk is shown here. I'll be discussing two domains that we explored during my thesis. We'll explore the human-robot team setting and sequential decision problems. And finally, I will conclude. The contributions highlighted in green are new contributions that were done after the proposal. First, I will talk about the human-robot team domain, where we developed the ACT, Delegate, or Learn framework. This was presented in ICA 2022, where it was a finalist for the Outstanding Interaction Paper Award. All right. So we're looking at a human-robot team setting where a human is working with a collaborative robot to achieve manufacturing tasks. Collaborative robots are amazing because they are safe for humans to work with, and humans can give demonstrations to them on the job to learn skills as and when needed. So robots can learn and improve with humans on the job. Right. So we will consider such a human-robot team on a factory floor, which gets a batch of Lego assembly tasks to be completed. The only objective of the robot is to help the human complete all the tasks and try to minimize the human's effort to achieve this batch of assembly tasks. Importantly, we're not telling the robot exactly what tasks it needs to do, and the robot will have to figure out on its own those tasks and also the skills which it may have to learn if it doesn't have them. Right. So in this part of the talk, we'll be looking at both a level 3 question and a level 2 question. All right. So an obvious solution to this problem would be to take a task allocation approach, where we look at the capabilities of the robot and the tasks available, and we assign the tasks that we believe the robot would be capable to do. So in this particular case, say the robot is capable of doing these L-shaped objects, we would assign these tasks to the robot. However, if I put on my robot learning hat, I would say that, well, this is a collaborative robot. I can give a couple of demonstrations to the robot, which can allow it to automate all of the tasks, right? So after a couple of demonstrations, the robot can now do all of them, which is fantastic because now I don't have any assembly tasks to do. On the other hand, anybody who has worked with robots knows that teaching robots is a very cumbersome process. In particular, in this video, you can see me giving a demonstration to the robot to do peg insertion, which was quite hard, right? So even giving demonstrations to the robot takes time. And in general, we don't want to be in a situation where we spend more time teaching the robot than the time we save through the automation that we get out of it, right? In particular, in this case, it's unclear why the human should teach the robot how to do this Z-shaped object at all, because there is no other similar object to the Z-shaped object in this batch. Hence, there is no future benefit coming out of this teaching. So this happens to be the optimal assignment, where instead of the robot doing all the tasks, it only focuses on these 5 tasks, and the human can take over the Z-shaped object. So the robot needs to decide exactly which tasks it needs to do, and also the skills it needs to acquire to make those tasks happen. Right. To solve this problem algorithmically, we propose the ACT, Delegate, or Learn framework, which models the high-level reasoning process through 3 options to the robot. Either the robot can do the task on its own, or it can delegate it to the human, or it can ask for a demonstration if it believes that there is a long-term benefit of getting that demonstration. All these options have associated costs. In particular, the cost of learning is the highest because that's the most typical problem. Compared to related work, so there are, we talked about the task allocation approach to solving this problem. There is also interactive learning from demonstration line of work. However, that does not take into account the option of delegating tasks to the human. By contrast, our approach combines both the benefits of both these approaches, which enables more efficient solution. So now the question is, how do we actually solve this planning problem? And in our work, we showed that this problem can be converted into a mixed integer program, which has to balance the cost of learning and assigning tasks to the human with the benefit of solving tasks. I will not go into the detail of this formulation because I presented it in the proposal as well. But I do want to show you the results. So we evaluated this on a set of Lego assembly tasks where the team had to stack Lego blocks on the base plate, and the robot was given a set of 15 assembly tasks to choose from. Overall, we found that compared to baselines, our approach did much better. For example, the task allocation at baseline, which was choosing just between the robot doing a task and the human doing a task, it ended up assigning all the tasks to the human because it didn't believe the robot was capable enough. By contrast, the learning from demonstration baseline only decided between learning and the robot doing a task, and it ended up asking the robot to get too many demonstrations, which overall increased the human's workload. By contrast, our approach balanced all the three options available to the team, reducing the workload of the human by 10 to 15%. All right. So this is fantastic that we were able to solve this difficult planning problem through a mixed integer program. However, solving a mixed integer program optimally is NP hard. So this may work for small to medium-sized problems, but for larger problems, we may have difficulty scaling this up. To address this problem, we propose an approximation algorithm to solve the ADL problem. In general, the idea is to convert the ADL problem into what is called a facility location problem. And I will get into the details of that problem in a bit. Once we convert it into a facility location problem, I can pick up my favorite approximation algorithm book and use a log n approximation algorithm to solve the facility location problem, which also gives me a log n approximation algorithm for the ADL problem. All right, so why do we care about this solution? First of all, we get a polynomial time complexity, which means we don't have to solve a mixed integer program to get the solution. And second, we are getting a log n suboptimality bound even in the worst case. Any quick questions? I'll take a water break.
Yeah, what is n in this case?
Oh, n is the number of tasks. All right, so let's try to understand what the facility location problem is. Right. So in the facility location problem, there is a universe of demands or clients that we want to satisfy. And there are potential facilities that we can open to satisfy those demands. You can imagine trying to open a gas station and making sure that the gas station is opened at locations which service a lot of clients, right? Opening each facility incurs a fixed cost. In this case, both the facilities incur costs of 10, right? Once the facility has been opened, it can then service clients through a service cost, which depends on how close or far it is from these demands. So for example, facility 1 has a service cost of 1 for all the clients. On the other hand, facility 2, which is located further away from these clients, has a higher service cost. The facility location problem is simply to minimize the facility opening cost and the service cost. So in this case, it's optimal to open just the first facility because it has less overall service cost to satisfy all the demands. So our strategy to convert the ADL problem to the facility location problem would be as follows. In our case, all the tasks that need to be done are customers that we would like to satisfy by solving them. And associated with each task, we will have two distinct potential facilities that can be opened, that is, they can be chosen. So let's consider the first task, the Z-shaped object. This has two options of either delegation or learning, and there are two potential facilities corresponding to the two options. Let's say in this setting, the cost of delegation is 100 and the cost of learning is 200. Typically, these are domain-dependent tasks, and we'll be getting these costs from the domain. Note that the cost of learning is higher because learning is a more cumbersome process. So once the task has been delegated to a human, the task is assumed to be solved, hence there is no other benefit coming out of it. However, when the task has been taught to the robot, there can be potential benefit if there are similar tasks to the task that the robot has learned. However, in this case, there is no similar task to the Z task, so the better option is to delegate. By contrast, if we look at the T-shaped object, we again have delegate and learn options. However, in this case, there are two additional T-shaped objects, meaning if we open the learn facility, it can, in addition, cover two assembly tasks. And in this case, in comparison, if we had chosen the delegate option, we would have to open two separate delegate facilities. So in this case, it turns out that it's better to choose the option of learning for the T-shaped object. Now, in general, how well the skill transfers to other tasks is a function of how similar those tasks are to each other. And we assume that we have a similarity function, which tells us how similar tasks are. In this case, of course, we are assuming that these T-shaped objects are all identical to each other. All right, so this brings us to our main theorem, which says that there exists a log n approximation algorithm for the act, delegate, or learn problem. Here, n is the number of tasks. And I gave you the rough outline of the proof where we convert the ADL problem to the facility location problem. And then we use existing results on the approximation algorithms for facility location problem to get similar bounds for ADL. Right. So there are two main takeaways from this part of the talk. First of all, empirically, we showed that a robot that is capable of planning what tasks it is doing and with skills it is learning can reduce the overall workload of a human significantly. And theoretically, we showed that our plan at ADL can be converted to a facility location problem, which gives us a log n approximation. Right. So to summarize, in this part of the talk, I started out by asking the question, given a high-level instruction to a robot to help a human in its domain, can it decide which tasks it needs to do and which skills it can learn? And we proposed a solution that takes a step towards answering that question. Right. So in the next part of the talk, I'm going to switch focus on decision-making problems, which are problems where a robot may have to sequence multiple skills one after the other to achieve the task. One of the assumptions that we made in the first part of the talk, where we were considering a human-robot team, was that the tasks were not sequential. So corresponding to every task, there was a single skill which could be learned to solve the task. And in this part of the talk, I will relax that assumption by allowing for skills to be sequenced to solve the task. Right. So in this case, we will assume that the robot has been given the objective of solving a distribution of tasks. And the only question it needs to answer is the exact set of skills it needs to acquire to solve those tasks. Right. Sequential decision problems are everywhere, right? You can ask a robot to fetch you a can of soda from the fridge. It will have to navigate to the kitchen, open the door if it's closed, open the fridge, locate the soda can in the fridge, and then take it out, right? And right, so however, no matter how much effort you put into designing such robot systems, when they eventually get deployed, there are always failures from a variety of sources. For example, on the left, the robot got a slightly inaccurate pose of the handle, which led to a failure. On the right, the robot was not able to grasp the can at the location that it intended to, and later on, this led to a collision with the shelf when it tried to place it on the shelf. Right. So in this part of the talk, we will be motivated by the problem of quick recovery from failures. So once such failures happen, we want the robot to be able to quickly learn recovery skills, which allows it to become more robust during its next deployment. We will consider the example of opening a door because it is so commonplace, where the robot already has a bunch of controllers for grasping, rotating, and pulling the door open. However, due to a variety of reasons, when it fails, it ends up in a failure state, which we define as a state which is not covered by the nominal controllers that the robot has. And the question then is, how can the robot recover from such failures, right? So once the failure has happened, the robot can either go all the way back to the start, or it can try to directly shoot for the goal. or perhaps it should go somewhere during to the middle of the task to recover from the failure. Corresponding to each such location where the robot could recover, there is a distinct recovery strategy that can be learned, but it's unclear what that recovery strategy is. Right. So the overall approach is going to start with a set of nominal controllers, pi1, pi2, pi3, and we will assume that we know the preconditions, meaning the states from which these skills can be executed beforehand. We stress test these controllers in simulation. Here you can see the robot trying to open doors from a variety of locations in Mojoko. Once a failure is discovered, we record it and cluster them to come up with a set of potential failure modes that the robot may run into during execution. The recovery learning problem then is to quickly learn recovery behaviors, which allows the robot to recover from each of these failure clusters back onto the nominal chain. In this particular case, every failure cluster has 4 potential recoveries that it can learn. All right. So the approach that we take to solve this problem is that of active skill learning. Right. So in general, there has been a lot of work on active learning of a single skill, where the robot strategically asks for the human demonstrator to give it a demonstration which allows it to learn faster. Right. However, so we will use a similar setting where the robot chooses a failure for which it wants a demonstration, and then the expert demonstrator gives it a demonstration to solve that failure. However, prior works don't directly apply to our problem because they have been designed for single skill learning. On the other hand, our problem is a sequential decision problem. So the robot may have to open the door, open a fridge to be able to finally pick up the Coke. And in this case, say the robot has 2 skills, pick skill, open skill, right? And both of them have their own associated success rates. It's unclear which skill the robot should be prioritizing to get better at the overall task. Should it be learning how to improve the pick skill, or should it be spending its time trying to improve the open skill? Right. So to solve this problem, we extend the prior active learning approaches by enabling them to work for sequential decision problems. And the main insight we had was that in addition to modeling individual skills, we also need to model the overall task to understand how relevant each of these skills are to the overall task. Right. So our approach, called meta reasoning for skill learning, has 2 key ideas. First of all, we learn a model of skill improvement for individual skills. So on the graph here, you can see historical data of how each individual skill is improving with additional data. It started with 60% success rate, went up to 70, and then went up to 78. Look, using this historical data, we can estimate the rate of improvement of this particular skill. However, the rate of improvement in learning is usually quite noisy, so we cannot directly use the mean of it. Instead, we estimate upper confidence limit of the rate of improvement and choose to use the upper confidence limit for optimistic learning. Right. Now, using this rate of improvement, we can then predict what is likely to be the success rate if this skill were to be further trained for another round. So using this historical data, we can predict that at the next time step, that is 5, the success rate would be 90%. Yeah.
So I thought the idea was you're going to failure state, you don't have any skills that apply.
Mm-hmm.
So how do you initiate this? Because you have no past data about this unknown skill.
Yeah, that's a good question. So you would have to you'll have to train each skill for a couple of rounds to get this data. In the experiments, we used 4 previous rounds of data to estimate the rate of improvement. Right. So you would need to train it for at least 3 or 4 times.
So in the example you gave, where you have 2 failures, each can go into 4 different places, you've got 8 potential skills. You have to train each of them 4 times before you can even start this.
Yeah.
So that's 32. Seems like a lot before you can start using your meta reasoning.
That is true. Yeah, so the quick answer to your question is yes. What you said is exactly how we do it. Unless you have additional domain knowledge, which can tell you what the rate of improvement would be. Okay, cool. So once we have the prediction for what the success rate would be in the next round, so say 90%, we still don't know how useful this is to the overall task. And to estimate the importance, we need the symbolic MDP of the overall task, where edges correspond to the success rate of individual skills, and nodes correspond to the precondition of the next state. So if we have this MDP, then we can run value iteration to solve this MDP with the predicted success rate. And that can give us a prediction for how much the overall task success rate would be. So let's see an example to understand this. So suppose the rate of improvement for the pick and open skills are 0.1 and 0.08. So in this case, the pick skill is easier to learn than open skill. With the rate of improvement prediction, we can predict that the success rate would go up to 80% after another round of training. In this particular case, the task MDP is quite simple. To estimate the task success rate, you simply need to multiply the individual success rates of these skills. So in this case, it turns out that the task success rate would go up from 34 to 39%, which is great.
Oh, okay. Go on.
Okay.
I was going to say, I wasn't sure that that was right, but I wanted to see, go on, show me the next.
Okay, sure. Right. Now, instead of the pick skill, you could have chosen to improve this open skill, which has a slightly lower rate of improvement of 0.08. So that goes only up to 78%. However, surprisingly, that leads to a much better improvement in the task success rate because the open skill is much more important to this task. The robot needs to use the open skill twice, right? So as we can see here, we need both information about individual task success rate and also the overall task structure to identify the correct skill which needs to be trained.
So it seems that there's one thing you're not modeling, which is what is the cost of recovering from those failures? So there's still whatever 20% chance of 22% chance of failing. It could be that recovering from the open task is much more expensive than recovering from the big cat.
Right. So the example that I gave you for the sake of simplicity only had success rates. In general, if you also have the costs, meaning if some certain policies are more expensive than the other, you can incorporate that, right? Because we're solving value iteration. So if we have the costs, we can compute the expected return, not just the success rate. Okay, so now we can apply that algorithm to solve the recovery problem that we had started with, right? So we had a bunch of failure modes, and we're trying to figure out which recoveries to learn. And if you apply the meta-reasoning algorithm, then it can balance both the relevance of each skill to the overall task and how easy it is to learn those skills. And at the end of the algorithm, you would find that the algorithm converges to the recovery behavior, which is the most appropriate for the task at hand. All right, so we evaluate this idea on the door opening task that I showed to you earlier, and we evaluated on a whole range of handles, both in simulation and real world. We compared executing the robot with the recovery behaviors on top of the nominal controllers that it started out with. And we found that in both situations, there was significant improvement in the success rates. All right, next, we also want to see how important the meta-reskill algorithm is for efficiency. So here we compared training the recovery policy using meta-reskill with training all the policies with equal weightage. And we find that our approach, shown in blue here, leads to much faster improvement in the performance than if you were to train all the recoveries with equal weightage. All right, now let's see how it works in practice. So the robot tries to open the door, initially gets the wrong estimate of the handle and is about to fail. However, we have our precondition classifiers, which tell the robot that a failure is about to happen. So we instead execute the learned recovery behavior, which in this case switches to a caging grasp and grasp the handle. And once we have recovered, we can then execute the remaining nominal controllers, which rotate the handle and open the door. All right, so this brings me to the end of this part of the talk. I want to highlight two key takeaways. First of all, we showed that by planning, a robot can actively decide which skills it should learn. And we showed that this leads to much more efficient learning. And second, we showed that by learning recovery skills in simulation, we can improve robustness of a robot in the real world as well. There are two limitations of this work, however. First of all, as I said, we need a symbolic representation of the overall task to compute the relevance of individual skill to the overall task. And second, we took an approach based on imitation learning, where we required an expert demonstrator to generate demonstrations for learning individual skills. In the final part of the talk, we will propose an approach which relaxes both these assumptions to some extent. Right. So here I'm going to talk about our algorithm called recovery chaining. This work was done partly during an internship at Mitsubishi Electric Research Lab with Devesh and Diego. And the idea here is similar to before, where we are trying to learn a recovery behavior, which can allow a robot to recover from failures, which are seen during execution. Right. And the approach that we take is that of using hierarchical reinforcement learning instead of imitation learning. In addition, I also want to highlight that we do reinforcement learning with just sparse rewards. So there's no reward shaping involved here, which was quite cool. Okay, so how do we do reinforcement learning in the setting that we are working with, right? So as before, we have a bunch of nominal controllers, pi1, pi2, pi3, right? And prior works typically assume that you know the preconditions. If you are on a failure state shown by the red circle here, you start your reinforcement learning agent from that failure state, and you provide a reward function which depends on the distance of that agent to the precondition that you're trying to go to. So if the agent is trying to recover to precondition 3, it may get a reward which is negative of the distance to that precondition, right? So if you have accurately learned the precondition, then this works, right? However, there is still an overhead of learning the preconditions. And in practice, we found that in our domains, learning the preconditions accurately is quite challenging. Even a small error in the precondition leads to wrong policies, and which prevents the robot from recovering. So we are going to make a key observation here, which is instead of having to pre-compute and learn the precondition, we also have the option of computing Monte Carlo estimates of the precondition by executing the nominal controller. So if the robot is trying to recover to precondition 3 and say it does not have the pre-computed precondition, it can simply execute a couple of Monte Carlo estimates, rollouts of controller pi3, verify whether or not it was able to reach the goal, and use that estimate to verify whether or not it is in the precondition. Right. So by using this observation, we propose the recovery chaining algorithm, which is basically a hybrid action space, which tries to answer two questions. The first question is, how should the robot recover when it is at a failure? So if the robot has run into a collision, say with the wall, then what are the immediate actions it needs to take to recover from the immediate failure? And the second question is, given this long horizon multi-step chain, in this example, precondition 1, 2, 3, and the goal, there are 4 options. Where exactly should the recovery agent try to recover to? So to answer the first question, there are primitive actions in the hybrid action space. This is pretty standard. These are actions that the robot takes in the end effector space to move around in the free space. However, we also provide the robot switch actions, which do exactly what I explained to you earlier. If the robot is trying to recover to precondition 3, once the robot takes a switch action, it executes the nominal controller pi3 and gets the reward based on whether or not the goal was achieved. So we have as many switch actions as the preconditions, as many preconditions there are that the robot may want to recover to. All right. So there are three benefits of this approach. First of all, we do not have to explicitly learn the preconditions a priori because the switch actions are using Monte Carlo estimates. Second, the reward function here is exactly whether or not the task was completed, so we don't have to use reward shaping. And finally, we can use online reinforcement learning algorithms, which, as I will show you later, can enable the discovery of novel recovery behaviors. All right. So we evaluate this in two domains, pick and place and shelf. In particular, in the shelf domain, there is uncertainty in the location of the box that the robot is holding. So the robot may collide with the shelf as it is trying to place. And we compare our approach, shown in blue, with the offline skill chaining approach that I explained earlier, where we started out with a pre-trained precondition, which is then used to generate reward for the reinforcement learning agent. And we find that the baseline approach almost always converges to a suboptimal policy, whereas our approach consistently and reliably improves performance. Right. So in both pick and place and shelf domains, we found that our approach significantly does better than the baseline. In particular, we noted that our approach does much better in the shelf domain. And my guess is that it's because we have partial observability here because of the uncertainty in the position of the box, which makes it more challenging. Right. So one potential for our approach for being less sample efficient is that we are not telling the agent exactly where it should recover, right? So for all the possible states that the agent can recover to, we allow the agent to choose on its own to make the optimal decision. However, we find that the agent is able to quickly identify the best precondition to recover to. Here, switch action 1 corresponds to recovering all the way to the start, and the other switch actions correspond to the other preconditions. And we find that pretty soon the agent is able to converge to switch action 1, which is the right precondition that the robot should recover to. And we see some interesting behaviors being learned with such a recovery agent. So here the robot first collides with the shelf, which leads to some in-hand rotation of the box as well. The recovery behavior first gets away from the immediate collision, then pushes against the back of the shelf to fix the in-hand rotation, which allows it to reliably recover. And second, the failure here was that the robot was not able to pick up this object when it is close to the walls because of collision with the wall. The recovery policy learns to push the object away from the wall and then finally pick it up. We transfer the learned policies to real world as well. Here, the robot first collides with the shelf because of incorrect grasp of the bottle, which leads to in-hand rotation of the bottle as well. And as you will see, the robot first recovers from the collision, and it's then going to push against the back of the shelf to fix that in-hand rotation, and then complete the task.
How does it perceive that there's an hand rotation? Is it vision?
No, no. So we use domain randomization and simulation. So
how did it perceive it here that it actually rotated? What if an object?
no, it learned a more conservative option of always fixing the slip.
So but it always assumes that if it does this, there will be rotation. Right?
Yeah. I mean that because that strategy is more robust than yeah. But if you had suppose extra sensing, which allows you to know whether rotation has happened or not, then it can be more efficient. All right, so the main takeaways from this part of the talk are that reinforcement learning, when it's combined with model-based controllers, can learn interesting behaviors even with sparse rewards. And second, we proposed a recovery chaining agent, which learns both how to recover and so to quickly summarize this part of the talk, we started out with the problem of learning skills, which are optimized to achieve a set of long horizon planning tasks. And then we discussed two algorithms, meta reasoning for skill learning, which is an active learning algorithm used in conjunction with behavior cloning, and recovery chaining, which is a hierarchical reinforcement learning agent. All right. So this brings me towards the last part of the talk, which is the conclusion. Right. So I want to summarize all the contributions that I made throughout this thesis. We started out with the high-level objective of enabling a robot to autonomously decide which tasks it needs to do and which skills it needs to learn to help a human in its domain. And to this end, we made 3 contributions. First of all, we proposed a plan to learn framework, which advocates for a robot to solve a meta-reasoning problem, that is a planning problem, to answer these 2 questions. We explored this idea in a human-robot team setting, where we proposed the first optimal ADL planner that jointly reasons about which tasks to do and which skills to learn. Then we explored sequential decision problems, where we explored active skill learning motivated by the problem of recovery from failures. And here we proposed 2 algorithms. The first algorithm, meta-reskill, is the first active skill learning algorithm in the context of sequential decision problems. And we propose recovery chaining, which is a hierarchical reinforcement learning for the same problem. All right. So I'm quite excited by the future directions that we can pursue in this area. In particular, my thesis lies at the intersection of human-robot interaction and sequential decision problems. And I believe there are exciting problems to be addressed in both those domains. The long-term goal, of course, is to enable the learning of human-aligned skills, which allows humans to have personalized robots. To get there, I believe we need to learn more human-aligned skills, meaning the robot should do tasks in a way that the human would like the tasks to be done. For example, if I ask my robot to unload a dishwasher, I would like the robot to know exactly where I prefer my plates to be or my bowls to be. And the robot would have to figure out on its own what those preferences are. One obvious next step is to incorporate such a reasoning process in the ADL framework that I talked about earlier in the talk. And we have made some progress in that direction with my collaborators, Pat and Michelle. The other direction I'm quite excited about is robust skill learning, right? So it's been quite evident that robots need more reliable and robust skills to succeed in the real world. And a lot of the work in the second part of my thesis was motivated by the idea of recovery from failures. I still believe that's a very important problem. And I want to build upon that to extend it to discover failures in the real world. In particular, we found that simulation, even though simulation can capture a lot of failures, it does not capture all the failures that the robot might run into. Also, creating simulation environments is time consuming. So ideally, we would like the robots to run into failures in the real world and then learn how to recover from those failures. The other direction that I'm also quite excited about is learning skills that are appropriate for partially observable environments. I spent quite some time on working at that problem, but it's a very hard nut to crack. I hope to keep making progress in that direction. All right, so I'm gonna end my talk by thanking all the people who have helped me throughout my PhD. I would like to start out by thanking my advisors, Max and Oliver. It has been a pleasure working with both of you. And I don't think I could have found a better combination of advisors. Max has tremendous expertise in planning. Oliver has tremendous expertise in learning and manipulation, and they share a common appreciation for robotics. So that was quite infectious. I started my research career working with Max all the way back in 2016, I think, when I was a summer intern in his lab. And yeah, you're
always welcome to come back.
Yeah, it's summer. Yeah, I remember reading his papers on LPS star and ARA star, and I was like, yeah, I want to do research like that. So yeah, I mean, your research has been truly inspirational. Thank you, Oliver. All I know about robot learning, manipulation, it's been from you. Thanks a lot for that. I'm always excited by the enormous range of research that you do, all the way from building robot hardware grippers to robot learning to controllers to even causal learning. So it's truly exciting to work with you and see how curious you are about everything under the sun. I want to thank Reed for the many discussions we had. Your feedback has been truly useful for the thesis, and I particularly appreciate your insightful questions. But I think yeah, they helped me a lot in improving the thesis and fine-tuning the ideas. Finally, I want to thank George. George's work has been truly influential in all my projects. If I count the number of papers I've cited in all my papers, probably half of them are going to be from George. So thank you, George, for all the fun discussions and inspiring me to pursue ambitious problems. All right, I want to thank all the mentors I've had over the years. I thank Chris and Leo for being on my qualifier committee. I want to thank Venkat, who was my summer intern mentor when I worked with Mac. One of the reasons why I did a PhD. I want to thank Oren. I want to thank Devesh and Diego for mentoring me last summer. It was a fantastic summer in Boston. I want to thank all my collaborators over the years. Tav, Kevin, Jackie, Mohit, Soumya, Pat, and Michelle. Thank you so much. I truly enjoyed collaborating with all of you, and hope we keep collaborating and doing fun research projects. Right. One of the perks of being co-advised is I get to be part of two fantastic labs, search-based planning labs, and a search-based planning lab and IAM lab. And I don't think either of these images have all the members, but you get the idea. I'm thankful to all the people who have ever been part of the labs and who I had a chance to interact with. And I feel like living away from home is always hard, and I feel like the labs here, SBPL and IAM lab, were almost like second homes to me. So really appreciate the support. Want to thank the broader RI community. I think RI is a truly special place for robotics. It's everybody here cares about robotics, but we are really so nice to each other. So thank you so much for that. I want to thank Rachel, who has been supportive of me throughout the PhD journey. Also want to thank Art and Salsa. That's a hobby I picked up at CMU at Art and Salsa, Latin dancing. So that's also been a source of joy in my life. And most of all, I want to dedicate my thesis to my family, my parents, and my younger brother. They have been constant source of joy and support to me. So thank you to them. Well, with that, I want to end my talk and open the floor for questions.
So can we start with what started the way?
Hi, Shivam, can you hear me?
Yes, I can hear you, Josh.
Yes, great. I just want to, first of all, wonderful work, and we've discussed this a lot, and you know that I think it's great. So I'm very pleased about that. I had sort of three small questions that are sort of separate from the larger questions we've discussed for a long time. And maybe these are a little they're smaller bore than what we usually talk about, but it's interesting to think about. One question I had was, for the first part of the skill recovery work, you said that you needed a symbolic representation because you were building that graph. And I wonder though whether that graph, because that graph's easy to construct in that case, right? And maybe it's not like a complete symbolic representation for planning, but it feels like, for planning with these things in an arbitrary way. But it does feel like it's sufficient for what you're using it, which is kind of, you think of this thing as almost a straight line sequence of execution through these skills. And so I wonder whether you think you need much more than that sort of graph, which you can construct automatically, right? It's not too difficult to put together from that data once you've got the initiation sets.
So I think that's the question, like how accurately can you get the initiation sets? right?
I see. Right, yeah.
And I think in manipulation, getting the initiation sets right is tricky for contracted stuff because contact is a very nonlinear event. So how do you make sure it's accurate enough? So I think the question is, assuming you have an inaccurate initiation set and hence an inaccurate task MDP, how useful can it be, right? And I'm not super sure what's the right answer.
I see, but let me just make sure I understand. So you're saying actually you think that graph is the right symbolic representation. It's just that the graph may not be accurate because you're right. I see.
Because the initiation set itself may not be fully correct, right?
Yeah. So actually that leads nicely onto my follow-on questions, because one way to think about making the initiation set thing more sophisticated is to make it a probabilistic classifier instead of a classifier. And the way to think about that is that now you have a probabilistic estimate of whether or not you can run a skill from a state instead of just a yes or no.
Right.
And so I wonder whether that will mitigate a lot of, it gives you like a stochastic, you build like a stochastic graph out of it in that case, but it gives you a more sophisticated kind of way of reasoning about the semantics of the stuff. And I wondered whether or not you had that framework where the agent was learning to choose which skill to execute next. And it was kind of learning that in a model free way, right? Like it really just tried everything.
Exactly.
But I wonder if we had that probabilistic initiation set, whether we could use that to bootstrap that, whether we could do something more sophisticated than just model free learning of that state.
Right. So I think if you do have such a classifier, then I think that's going to be much better than the model free approach that I presented. But I think the main question is how do you know whether or not the initiation set classifier is accurate enough? And what do you do when you need to evaluate it in out of distribution states, right? But
if you've got a good probabilistic classifier, it should sort of do the right thing, right? Like it's kind of the probabilistic classifier's job to handle that generalization appropriately, right?
Right. Yeah. I agree. I think if we can get the right classifier, then doing the more model-based approach with the preconditions is the right approach.
Because I really like the idea that you had, which is that the agent gets to choose when to trigger the skill switch. It doesn't just happen because the initiation set says so.
Right.
I really like that. I just wonder whether or not, because you could say, oh well, let's put an action prior that says like use the probabilistic classifier as an action prior, and then if it's wrong, you'll learn a way where you switch. But if it's right, then you get zero shot basically.
Exactly. So I think an action prior is a great idea because it's not constraining the agent to only try an action if the precondition is satisfied. So we want the agent to also explore a bit so that if the precondition is giving it the wrong answer, there is eventually, hopefully, the agent would figure out the right answer.
Yeah, it's a natural way to get around it. Yeah. And then that brought me to my third question, which was that you were talking about POMDPs and because I noticed several of your failure modes were in the real robot videos were because there was like inaccurate tracking of the object or something like that.
Yeah.
And so there I wondered whether you can go full POMDP and there's a belief space and everything is really complicated and that seems like a nice thing. But I wonder if there's an intermediate way where you could think about, you could think about like, if you've got a fairly narrow distribution of state, whether you could keep everything else looking like an MDP, but just think about expectations over that distribution in the initiation set, right? If you could do something sort of halfway.
Right. So the practically the approach that worked well for those problems was the more, I guess, conservative, robust RL approach, where you train the policy over a whole range of uncertainties and failures, and eventually the agent learns something more conservative. So, for example, in the shelf task where there was both collision and in-hand rotation, and there was no way to observe the in-hand rotation, the policy simply learned a more conservative strategy to always push against the back of the shelf. And that was not a POMDP solution per se, but was still able to handle those failures.
Yeah, which is really cool, right? I mean, it's even better than because a POMDP solution is unhappy, right? Usually, but you're getting the effect of it without having to deal with the computational explosion, which I think is magic. And so I wonder whether there are other ways in which to get the effect of a full POMDP without having to actually POMDP.
Right. Yeah. I mean, I agree. I think that's a very interesting question.
Yeah. Anyway, yeah, I thought that was cool and a fun thing we can think about exploring. Anyway, those are all the questions I have. As I said, I think it's wonderful work, and I love all these papers, as you know. So, congratulations from my side, and I yield the floor to whoever's the next furthest away person.
I'll also say, really great work. Enjoyed all our discussions with you. I have one detailed question, one high-level question. So that's the detailed one first. From what I understand, and I might be wrong, so correct me. From what I understand, for ADL, you need to know the sequence of tasks that are going to be performed.
Right. Yeah.
Do you have any idea of how it could be extended if you have a distribution of tasks?
Yeah. So yeah, I think that's a great question. We have thought a little bit about it. So I think there are two natural future directions. One is when there is no fixed order to the tasks, but there is still a finite set of tasks. So there you could imagine also actively choosing which order to do the tasks. And there I think the mixed integer program approach might work. So in the current formulation, we have constraints which enforce the sequence.
So let me just ask, so why would it matter for ADL, the order in which you do the tasks?
It matters for learning, right? So if you learn task 10, it only helps you on future tasks, right? Whereas if there is no order, if you can change the order, then you could have learned the 10th task first, and then you would have got the benefit on the first 9 tasks, right? So if there is no, if you can,
but why wouldn't you learn the first task first and then you still get, or is it asymmetric? You think there's asymmetric generalization?
So it's not about asymmetric generalization, right? So let's say we have the Z-shaped object, right? Say we have, there's a Z-shaped object on task 10, right?
Okay.
So learning that task is not going to help you on any of the first 9 tasks, even if there is another Z-shaped object there, right? So the benefit of learning is only if you learn it, say, on the 4th task, then that helps you on the 9th task, but not vice versa.
So if you have multiple Z's, right?
Yeah.
The first time you get to the Z, you learn it. If there's going to be future ones, doesn't matter which task it is. Let's say the T's. So there's different types of T's, right? Does it matter, like, if you learn the long T, it'll help you with the short T, but if you learn the short T, it wouldn't help you with the long T? Or, the first time you get any T, you realize that there's going to be N ones subsequent, and you just learn it then.
Yeah, but
that's why I'm asking you, does the order matter?
Yeah, that's a good question. So in the current framework, it does not. We assume a sort of symmetric task similarity.
Okay.
But I think more generally, it should matter, right? If you were to model it accurately, then those things would come into the play. And then the question is, how accurately should you model?
Anyway, so going back to the main question, you said that you thought about extending ADL to a distribution of tasks. Can you say something about what you think that would look like?
Right. So I think, okay, so 2 answers. If all you have is the distribution, then you don't really know like the exact number of tasks of the, suppose there are 3 different categories, right? T, L, and Z. If all you have is the distribution, the answer would depend on how many tasks are you going to solve.
What is the expectation?
Right. So you could maximize the expectation, right?
Mm-hmm.
So I think that would be the approach to solve that, but then that's only a locally optimal solution. So if all you have is the distribution, then we can probably come up with a locally optimal solution which maximizes the expectation. The great thing about ADL is that if you have a discrete set of tasks, you can ask, can I optimize it globally, right? Can I get the optimal solution, which is not just locally optimal?
So I'm just thinking about, your domain, your human, household robot domain. It's really unnatural to think that for the life of the robot, I'm going to tell it in advance all the tasks that it's going to do.
Right. Yeah, that's a good question. I think so. One of the motivations for ADL was a factory setting where you get a batch of tasks in the conveyor belt, and for the next week what the batch of tasks is going to be. But I agree that
Again, the robot, so you don't throw the robot out of the week. The week after that, it's going to get another batch of tasks. The week after that, it's going to get another batch.
Right. Yeah, I think I agree. I think the idea of having a distribution is important. Yeah, definitely a problem that I will look into.
But do you think you would sample from the distribution and then solve the ADL problem multiple times and then, compute the average? Or?
Well, I mean, I think, so that's one way to do it. But I think there could be even simpler solutions, right? Where you just pick the option that immediately maximizes your expected return over the entire distribution, right? So it's unclear if solving the whole ADL mixed integer program is the right approach in that situation.
So my general question was limitations, which is different from future work. So
Yeah.
For the two main sections, can you talk a little bit about the limitations that you've observed, or theoretical limitations?
Right. So first of all, I would say that there are a ton of limitations. So
That's better than just sitting there and saying, no, there's no.
right. So for example, in the human robot team setting, even though, eventually I want to have more human robot interaction, the interaction in that is at a very limited setting, right? Just the interaction is basically who does what and then learning. So clearly, if you want this to work in the real world, there has to be better communication, more avenues for collaboration. I mentioned the idea of incorporating preferences. So the way a human may want a task to be done may not be known to the robot. So the robot may have to actively ask for that. But perhaps the biggest limitation right now is in the ADL framework, we are only allowing for single step tasks. So you get a task and you have one skill for that particular task. But ideally, you want to be able to handle sequential decision problems. So basically, the work that I did in the second part, combine that with the first part so that we can handle sequential decision problems. Right. And in the second part, right, so we were looking at sequential decision problems. So I think throughout those two projects, I was very interested in the idea of partial observability, but we still haven't found a good solution that directly tackles that problem. So I think there is a lot of room there to reason about, to learn policies that say can work in belief space or somehow model the notion of uncertainty, which we don't model yet. Yeah.
No.
Nice presentation, and I know the work, so. Let's see, for the ADL, and actually, I'll have a follow-up question on the distribution. If you don't have a preset number of tasks, but it's more like, in the lifelong, what are the skills to learn? Wouldn't that be the case that you just want to learn pretty much all the skills that are on the table, so to speak? Because I mean, there's even the ones that are kind of unlikely, in the lifelong, they're going to have a lot of those coming up. So it needs to be probably coupled with some sort of a duration of over time, or which you're looking at it, right?
Right. So I agree with that. I think whether you have so you have a task distribution, and whether you have 10 tasks for 1,000, that changes the solution, right? Yes, I think we would need to be able to model the number of tasks that need to be done in the future, right? I think even that would be enough to make that decision, whether it's like 10 or 1,000. Just with that, in addition to the task distribution, you can make that decision.
Right, or if it's within the entire zone, probably there's some sort of discounting in there, right?
Right, yeah.
In the you know, like with respect to those skills learning, I would imagine that in many cases, even though the tasks are dissimilar, right? You know, different tasks, they're based on some sort of similarity, one could bootstrap using the policies from the other task, right?
Right.
And in other cases, it's more like you're looking at the problem of extending the policies as opposed to doing these. So, how would that, you know, your approach really was important?
So is this in the context of KDL?
Yeah.
Yeah, so I mean, right now we assume we learn separate skills for each task, right? I guess I don't have a great answer to that right now, because first of all, you need to answer how many skills do you want to learn? Like at which point do you decide I'm going to learn a new skill for this particular task, as opposed to improving a pre-existing skill. And in general, I don't think there is like any good solution to that. You could, you know, cluster the tasks a priori and say, okay, for every cluster, I'm going to learn a separate skill. So I think that we could do, right? Like given the batch of tasks, so we could cluster it based on say, L, T, and Z, and then for every cluster, we could have a separate policy and assume that there is no sharing across clusters. Yeah.
All right. For the recovery skill learning, the current formulation doesn't take into account the actual cost of learning itself. I think there are different skills that with different costs associated with the learning. Is that easier or difficult to incorporate?
Right. So right now the setup is every time you choose to learn a skill, there is a fixed cost associated with getting a demonstration for that particular skill. I guess, yeah, so I guess you can extend it by saying I have different sources of demonstrations which have different costs, right? I think that can be incorporated in the framework we have, because when we compute the benefit of each skill, it's the benefit is improvement in task success rate. You could divide it by the cost of that, getting that improvement, and then greedily pick the option which improves the task success rate per cost.
Can I just jump in, because I wasn't gonna ask this question, but it's follow on. So why doesn't the ADL framework depend on the likelihood of success at the learner?
Success of
Learning of this, the probability that once I learn this task, what is the success rate?
well, it does depend on that.
Oh.
Yeah.
Okay.
So the assumption we make is, well, when I learned task A, I assume I'm going to be perfectly competent on A, but the generalization is probabilistic. So I learn it on, say, one L-shaped object. It may not transfer fully on other L-shaped objects. And that depends on the similarity between those objects.
Right, so the question is, why make the assumption that you learn it perfectly? I mean, all the rest of your work says you don't learn the skill perfectly, and yet here you're making the assumption that you can't learn the skill perfectly.
Right. Well, so to be more precise, we assume, once I ask for a demonstration for, say, the current task, that task is done after I choose the learn option. In practice, that may mean that during the part of demonstration, the human also completes the task. Right. So, well, we made that choice to keep the framework simpler. If you don't choose that constraint, then it becomes a little more complicated.
All right, so let's assume that when the person does the thing, they'll do it perfectly. I'll grant you that.
Right.
But then, okay, but even for the skill that's been demoed, you assume that it's going to be learned perfectly, so it can be done perfectly afterwards, and how difficult would it be to extend that to say, well, there's only some probability.
Yeah, so we only assume that the task for which the demo has been sought, that is done perfectly. But for all the other tasks, we allow a probabilistic success rate.
It's like cost of failure, and hidden that the cost of failure is actually expectation. Which one of the cost of, like the probability of failure times the cost of fixing that failure, which is R. Okay. One last question from me, or on a broader level, like that, last slide with the future directions of the things that you're excited about and all that stuff. So, from your perspective, the bottleneck to autonomy, really, who is all that stuff, but still robots are not there.
Yeah, this is all teleoperated.
So the bottleneck to autonomy, is it in how we learn those low-level skills and including how to learn them better, how to do inference better, how to combine it with a model-based low-level control and planning, or is it in the questions of which skills to learn? So it's like, how do we learn the skills versus which skills do we learn? And where is the bottleneck?
Right. I mean, I think there is, I think both of them are challenging problems, right? So, I mean, first of all, of course, all the skills that the robot has learned, they have to be robust and reliable enough for the task at hand. So I think robustness of individual skills is sort of a prerequisite for anything interesting that the robot has to do, right? And the question of which skills to learn, that is more tied to the efficiency part of it, right? So like going from 70% success rate to 90% is relatively easy, but every time you try to improve a particular skill by 1%, it becomes much more harder, right? So if you want to really hone the skills that are required for your domain, then you have to really pick and choose about where you spend your time. So I think the question of which skills to learn, that's more tied to how we can do it efficiently, right? And I mean, in practice, if you had infinite resources, you would just learn everything, right? But in reality and in practice, I think both would be required.
So, which skills do we do for that?
Right. So, if you're in a domain and, juggling is also an interesting skill, but, if you're a household robot, maybe kitchen robot, you have to focus on kitchen tasks, even though juggling could be entertaining, right? So.
All right, thank you.
All right, I have a follow-on question for Lauren, because in your demo or your example, you showed like, go from like 70 to 80%, but maybe also shows that in sequential tests, you really need to be in that 99 perspective, right? And so I was just wondering, like, when you go from like 99 to 99%, like at that level, do you foresee maybe challenges for your framework? Like which goes to
Right. So I think like the primary challenge would be so the framework we had was all based in simulation, right? So we discovered the failures in simulation and learn in simulation. There is a sim to real gap. So the failures that you're going to see in the real world may not even be modeled in the simulation. So to truly achieve that 99.9, I think you have to discover the failures and learn the recoveries in the real world. I think that's probably the biggest gap there. And I think, recently researchers are exploring more continual learning and real world learning of skills. So I think that's the way to go.
For the ADL framework, so let's say the task similarity is very important.
Yeah.
And I kind of wanted to know, like, how you see that being done in the future. Is that like also kind of like a metal reasoning, like on top of it? Is it self-supervised? Is it what is that?
So I think it will depend a lot on the domain and whether you have data which can be used to learn the similarities, right? For example, in assembly domains, you can imagine there is domain knowledge in the factory workers, and they can give you some information about how similar and dissimilar tasks are. For more commonly occurring objects, perhaps we can leverage other modalities like language to understand how similar or dissimilar they are, right?
There's like a lot of like the subtleties. Like, oh, it's not really easy. They might be the same, but it's real problem.
Yeah, so I don't think we can ever fully accurately capture the similarity. I think that's too much to ask for. I look at the similarity as a rough measure of how similar the tasks are. Right. So there's a, yeah, I don't think we should be trying to achieve like exact similarities. Yeah.
And so, one last question, and, you mentioned that you did my work on VP.
Yeah.
And I mean, on board as a field, I was wondering if you have any advice for future students that want to explore on VP, lessons to learn.
We don't do it.
Yeah. So. Okay, so yeah, first of all, POM-DPs are hard, no doubt about that. And I think surprisingly, what I found was that the like prevailing wisdom in robotics is sort of right. The prevailing wisdom of handling POM-DPs is sort of right, So, which is, you know, like in general, if you can avoid POM-DPs, avoid it. But if you want to, you know, actively reason about the POM-DP, then you have to be super focused on, okay, what's the source of uncertainty, and try to sort of simplify the problem as much as possible, right? In practice, I found that the approach of estimating the belief state is the better approach. I tried an alternative history-based approach where you use recurrent neural networks based on the past history and try to do it more implicitly. That does not work. So I would, you know, stick to what's been shown to work in robotics. Yeah, so simplify the problems as much as you can, and yeah, I build on prior work on robotics.
And we open up to the audience. I noticed that I think you used an upper bound on the ROI.
Yeah.
I was curious why.
Right. So the rate of improvement is not constant, right? So it's a noisy variable, right? And suppose you ask for, you improve a skill, and suppose you don't see any improvement, right? And if you just use the mean, then that's going to tell you that, okay, avoid this skill. It's a really bad skill to have. But if you're computing the upper confidence bound on some, on a like a number of samples, then that may tell you that, okay, there's some variance. So let's not fully trust the one sample that we had.
Oh, so it's then upper bound as the number of the ROI.
On the ROI, yeah.
So are you being pessimistic or are you being optimistic?
I'm being optimistic. So I'm being optimistic about how much it will improve in the next round. If there's a lot of variance in the ROI, let's just say optimistically, what's the best I can get?
Yeah. Isn't that a bit risky?
In what sense?
Like in some ways, assuming that an optimistic estimate of how fast it are.
Yeah, so I mean, it's optimistic. So, you know, you would pick that option and then say it's actually not as good. So then you would update the ROI as well. So it sort of gives you completeness, I guess. You would not pessimistically avoid potentially good skills. Yeah.
Is this really famous speaker? Kick everyone out, get to stop the recording. Yes. And let's go over to the